Thanks, Rajiv. I'd like to thank the organizers for the invitation, and I'd like to also thank the previous speakers, especially Fabio, for discussing the constraints on inflation from the latest Planck 2018 data. I'll be not discussing much about those things, but as Fabio mentioned, I'll be covering the possibility of features. So I'll be talking about the possibility of primordial features that, or in another sense, you can think it as of the finding the details of the primordial power spectrum generated during inflation. And the base probe, as Fabio mentioned, that can constrain the primordial power spectrum is till date is the cosmic microwave background. And here in this slide, I have provided the maps from three full sky cosmic microwave background missions, COBE, WMAP, and Planck. To the left, you can see those. And to the right, I have plotted the angular power spectrum that you can calculate from these maps. So actually, you are taking the anisotropies that you can see with respect to the uniform temperature of 2.7255 Kelvin around across the sky, and you correlate them in and plot that correlation in various angles. Here I have plotted in the multiple moments that are related with these angles. And you can see that here in the dashed, okay, let me just turn on my pointer so that I can point to the places. Okay, so in the dashed lines, I have plotted the noise level of each experiment or each observation, to be precise. So here the noise level for COBE is provided, for noise level for WMAP, and noise level for Planck is provided here, as you can see. And for a futuristic mission, which is recently approved, the Lightbird, the noise level is provided here. As you can see that with the improvement in the noise level, that we can, if we increase the sensitivity of our instrument, and also if we can see the universe in a better resolution, you can detect the features in the power spectrum, in the angular power spectrum. These features are will be different from the features that I'm going to talk about. I'm going to explain that in more detail. But you can think it as of the screen of your TV. So earlier we had this standard definition TV. Now after that the high definition TV came in, and now you have ultra high definition TV, in which you can see any picture with finer details. So this is what we are trying to achieve. So from 1990s to 2013, we got COBE, WMAP, and Planck, and also various ground-based CMB surveys, which actually came in and has enlarged our scope, enlarged the cosmological scale that we can probe. For example, here you can see the temperature anisotropy power spectrum. We could only see from the COBE only the largest scales. For example, low L corresponds to largest scale, and the high L, as you go towards high L, they correspond to intermediate and small scales. After that, when WMAP came in, we could detect some part of the E mode polarization anisotropy using the WMAP full sky survey. And when Planck came in, we could actually see within one mission with 9 frequency channels, we could see the cosmic microwave background angular power spectrum ranging from 90 degrees to a very small cosmological scales. For example, 0.07 degrees or so, that corresponds to L equal to 2500. So the Lightbird is another futuristic thing. One thing that we have not seen yet is the B mode anisotropy, which is directly related to primordial B mode anisotropy, to be precise, which is related to the primordial tensor modes that can be generated during inflation, and which actually gives you the direct handle on the energy scale of the inflation. We are hoping that with Lightbird, whose sensitivity goes lower than 10 power minus 3 tensor to scalar ratio, corresponding to 10 power minus 3 tensor to scalar ratio, we will be able to detect such primordial tensor modes. And after that, we have also CMB. Let me just give you a brief discussion on the CMB Bharat. CMB Bharat is a near ultimate CMB mission that we have proposed to ISRO in the year 2018, and this is presently being reviewed, and its PI, Professor Tarun Soradeep, is going to talk about CMB Bharat in detail in his talk in the next days. As you can see that here also the noise level, what CMB Bharat does is that with its noise level, very low noise level compared to all the observations before, and also its high resolution, it can cover a large part of the spectrum that is unseen till today. As you can see that we will be able to see much smaller scale with much better accuracy as well. So now let me talk about the primordial pulse spectrum and its connection to the angular pulse spectrum. So if you have a inflation with a potential that allows the field to strictly slow roll down to its bottom, then the power spectrum that you can get is actually featureless and can be explained by a power law form over certain range and with certain tilt, the spectral tilt we call NS. And what we do is that we, for a forward modeling, we actually take this kind of power spectrum and we compare with the data that you are, I have plotted from Planck 2013 data here. We compare it with that and we get the constraints on the amplitude and the spectral index and also their derivatives and try to see that whether we can constrain them or not. So this is the brief history of the constraints on the spectral tilt from WMAP to Planck. As you can see here, these ellipses, these tilted ellipses here, or half ellipses, you can say, to be precise, correspond to the constraints on the NS spectral tilt and the tensor to scalar ratio. So since it is open, the ellipse is not closed here, that means that we have not detected the tensor to scalar ratio yet. And here we can say that with WMAP only we could discard certain part of the NS. So NS greater than, very greater than 1 were already ruled out. If you add some small scale CMB measurements and other large scale structure observation or H0, you can break the degeneracies and you can get the constraint, get much better constraint, which actually rules out scale invariant spectrum. So here, okay, so here, as I have said, NS equal to 1 implies a complete scale invariance. With Planck, just with Planck, which is a full sky CMB survey, if you don't include any other measurements, we have been able to reject a complete scale invariance by 8 sigma. Fabio also mentioned that in his error bars on the NS. As you can see that these are the confidence ellipses. If you keep on drawing these confidence ellipses, that means that your confidence in rejecting models are much better. So these are 2 sigma. Now, if you add 3 sigma, 4 sigma, 5 sigma, you will see that at 8 sigma, the ellipse will touch point NS equal to 1. That means that by NS equal to 1 is rejected by 8 sigma confidence only with Planck. Okay. Now, let me talk about the simple test of the scale dependence, whether the scale dependence of the spectral tilt, whether the tilt, the constraint on the tilt is completely same across all the scales or it is special to some scales. So for that, we tried a method of optimized binning in this paper, where we break the power spectrum in different parts. For example, we break the power spectrum at largest part and smaller parts or intermediate parts here. And we try to see the broad feature of the primordial power spectrum. As you can see that it doesn't have one tilt, it has 2 tilts or several tilts that can happen depending on your binning of the primordial power spectrum. So from the comparison with the data, you can plot the tilts of the primordial power spectrum that are allowed by the Planck data. This is done with Planck 2013 data, and as you can see that we have a limit up after which limit in the K after which the NS has to be red. That means your NS has to be less than 1, and if it is greater than 1, we call it blue tilt. Okay, so before 0.01 megaparsec inverse, at large scales, we can see that our power spectrum actually, our data actually provides the power spectrum with a blue tilt. However, after 0.01 megaparsec inverse, all the power spectrum, all the data constrain the power spectrum to be strictly red. So yes, we have a red tilt, but the red tilt is constrained after 0.01 megaparsec inverse. Now, I just talked about the constraint on the primordial power spectrum in a broad sense, the broad features in the power spectrum. Now, if you want to understand the small scale, the features that are localized to certain scales, that cannot be done in a broad search. For that, you need to do a reconstruction or some forward modeling. So here I'm going to discuss a reconstruction algorithm, the Richardson-Lucy algorithm. So as I said, again, this is the algorithm, this is the forward modeling algorithm that you have a nearly scaling invariant power spectrum, you compare the data. This GLK actually convolves with this PK of I is this one, then gives you the CL theory, okay? So then you compare that CL theory with the data. And this GLK is the matrix that that actually maps the K space to the L space, and the matrix looks like this. I'm not going to discuss much about the matrix, just to say that I would like to mention that this matrix depends on the background cosmology, the constituents in the universe, the H0 and all. Okay, now we are going to reconstruct the primordial power spectrum. We are using a modified version of the Richardson-Lucy algorithm, specially suitable for Planck, which has 5 different spectra for parameter estimation. This method says that at any iteration, this is an iterative reconstruction. It says that at any iteration of, let's say, I plus 1, the power spectrum reconstruction can be given as a correction factor to the ith power spectrum. So you can start with any initial guess of the power spectrum, and you iteratively improve on that, and you try to find what the data indicates. What we see here for different Planck frequency channels, for example, this is the Planck power spectrum at the largest scales, and these are the combination of the Planck frequency channels. These are the large scale Planck power spectrum. A corresponds to 100 gigahertz and 1 corresponds to 217 gigahertz. So if you combine them, you can find the certain hints of the primordial power spectrum. Definitely there are noises, but the hints are that there can be suppression in the tilt, suppression in the power spectrum at larger scale, what we have seen in the broad reconstruction as well, that there are hints of the blue tilt at larger scales. Now, to rule out the noise levels, we did a search with the by varying the Planck data, and we did the reconstruction by varying Planck data for 1000 Planck power spectrum generated from the Gaussian noises. And you can actually here plot the 68% and 95% confidence level. And what you can see that if you are doing a residual search, this red line you can think of it as a power law or the baseline model, and the fluctuations from there are actually the hints of the features. Okay, the features that you can see here, there are not many possibilities of features, localized features. For example, here is one which has nearly 2 to 3 sigma significance, and others are nearly 1 to 2 sigma significance. So we couldn't do better with Planck, or you can say that we didn't find any hints of deviation of the slow roll power spectrum, slow roll potential. So standard model assumption, power law is consistent at all scales apart from few localized oscillations near L equal to 22, 200 to 300, and 750 to 850. So these are the scales just to mention. Now let's come to the forward modeling. So as I said, the power spectrum that you can generate is coming from an inflationary mechanism. The mechanism is the slow roll mechanism, where the scalar field rolls down to its minima in a nearly flat potential, and that gives rise to the nearly flat primordial power spectrum. And here the some of the primordial power spectrum that Planck has compared. Fabio has talked about that, so I'm not going to that in detail. Here's something that we had compared with the WMAP data, and afterwards people have also compared these things with Planck data. So these are intermediate or initial moderate fast roll within the inflationary epoch. So the scalar fields rolls briefly, scalar field fast rolls instead of the slow roll briefly. So the inflation is still happening, but for a few E folds, for a few brief period of time, the inflaton or the scalar field is allowed to have some fast roll or the brief departure from the slow roll, let's say. For that, you can have this kind of suppression, and you can have wiggles in the power spectrum as well. So these are the different kinds of features that you can generate, like suppression, wiggles, and non-local oscillations. And you can also have this kind of a typical unique spectrum like log sign oscillation that can be obtained from a multifield inflation. You can so all these spectra give better fit with respect to the power of the primordial power spectrum, but none of these are statistically significant enough. So this is the this is the story till now, that we have not been able to find any statistical significance, any substantial statistical significance of any type of features. We tried to make or construct a framework of the inflation potential that can generate features that are hinted by the reconstruction, that separation, some localized oscillations, and some non-local oscillations afterwards as well at small scales. So this is the mechanism that you have a moderate fast roll which goes to a strict slow roll after some point of time. The Vs is the strict slow roll, and you are modifying the fast roll power spectrum, fast roll potential, with a parameter gamma. So we call it whipped inflation potential. You can keep on modifying that by saying that the scalar field transits from a moderate fast roll to a strict slow roll through a discontinuity. So discontinuity actually gives rise to these wiggles. And we came up with this Wiggly Whipped inflation potential, which has which can offer a huge spectrum of the features. For example, you can get primordial power spectrum that has that is step-like, that has a sharp cutoff, that has one dip, that can have some non-local oscillations and some localized oscillations and non-local oscillations, and at the same time you can have a combination of all this. So what is the usefulness of the Wiggly Whipped inflation? So it says that if you have one single framework of the inflaton potential, you can just throw that into your analysis, and within one analysis you can get what are the possible features in the data. Okay, so we tried to compare that with the Planck data, and we found that there are 4 local base fits. Out of them, one is the global fit, and we call it WWI A, B, C, D for simplicity. And you can see that there are different types of features: a dip, which fits the large scale features, and some non-local oscillations. You can have an oscillation that is persistent at to the very small cosmological scale proved by Planck. You can have some other type of oscillations here as well. And you can have Wiggly Whipped inflation prime, which gives you a discontinuity in the derivative of the potential instead of in the potential. So these are all features that gives you a 7 to 14 improvement in fit with an expense of 2 to 4 extra parameters compared to the standard baseline models. And at the same time, it just doesn't fit the outliers, it also fits something else. For example, if there are some tensions in the data, features help in fitting those as well. Here I'm talking about one particular apparent tension. It is not a particular, which is not a real, it may not be a real tension. As you can see that this is the constraint on the omega baryon content, the baryon content in the universe. And the constraints are given in the blue from temperature, and in the red are polarization. As you can see, the red, the central value of the red is outside, is rejected by this by the temperature data. But at the same time, you have to see that the polarization data doesn't have the same sensitivity as the temperature data. It is not as accurate as the temperature data, so it has a larger error bar. So you can see the Gaussian is much more fatter compared to the thin TT constraints on the baryon, omega baryon square. But still, it contributes in the chi square, the fit to the data. So if you have this kind of our model, Wiggly Whipped inflation, it tries to keep both of them in the same place. I have when you analyze with the Wiggly Whipped inflation, the baryon differences, the difference in the constraints in the omega baryon or the baryon density in the universe comes closer. So actually, whatever, if it is an apparent tension, it tries to resolve that tension by introducing these features. Okay, so now we also, so till now I have been talking about the 2-point correlation function only, but at the same time you can ask what is the 3-point correlation function of the primordial fluctuations. So the 2-point correlation functions are the power spectrum, the 3-point correlation functions are called the bispectrum. For a strict slow roll inflation, using the Malthus-Sena formalism, we calculate the FNL, the parameter that describes the bispectrum, which is the ratio of the bispectrum and the product of the power spectrum. It is found to be nearly 0 for a strict slowly rolling canonical scalar field driven inflation. But if you have features like Wiggly Whipped inflation or so, you can generate scale-dependent non-Gaussianity or scale-dependent FNL. What I'm showing you here is the equilateral, the FNL in the equilateral case where K1 equal to K2 equal to K3. In the top panels for the Wiggly Whipped inflation A, B, C, and D, these for these, and you can see that you can generate a high level of non-Gaussianity. Definitely, a high level of non-Gaussianity is discarded by the Planck data, but these are different templates, so it is not the same as the local non-Gaussianity or the scale-independent non-Gaussianity that goes in the Planck analysis. Planck analysis also deep take into account the scale, the oscillatory forms and things. Possibly if you do a joint analysis of this, there are some hopes that if some of the features are real, they will also contribute to the FNL and they can be detected in a joint estimation in this oscillatory template. So you can see that here I have plotted for a arbitrary triangular configuration, I have plotted it as a function of K2 by K1 and K3 by K1. Again, as you can see that the FNL can go as high as plus minus 600. But again, these are oscillatory templates and you have to compare them with the data in a different way. Now let's turn to the forecast. So there was a mission proposal called Core M5, which did not get funding from the European Space Agency, and improving on that, CMB Bharat, the concept of CMB Bharat originated. When Core was still under review, we started this work that if some features represents the true history of the universe, let's say, we call it a fiducial model. What does it mean is that we have not detected any features yet, but there are hints on the features. So if any of the hints represent true nature of our universe, let's generate the data from that type of feature, and using the sensitivity of a future CMB experiment, CMB observation, we try to see whether some of these features can be constrained or cannot be constrained. Definitely, it is a forecast. It is not a constraint on the model itself. It is a prediction. But you can gain a lot of information from there. For example, suppression. So let's divide our feature that we had seen between suppression and wiggles. We have a large scale suppression hint, and we also have a hints of wiggles, right? So what we can do is that we can generate from Wiggly Whipped inflation the mock data or fiducial from the fiducial power spectrum. You generate this mock data, and you do a Markov chain Monte Carlo. You compare your model with the data again, and you try to ask whether which type of feature can be detected in future. For example, this zero line. Okay, zero means that no feature or no suppression here. Here is zero line. Zero line means there is no wiggles. There are no wiggles. Okay. So which are defined by these two parameters, phi 01 and gamma. And remember, this gamma enters in the Wiggly Whipped inflation parameters and phi 01 too. As you can see that the suppression, even with a cosmic variance limited survey, such as Core, you will not be able to detect primordial suppression in the primordial power spectrum at large scale. Why? Because you have this cosmic variance dominated regime, which will not allow you to, even if you bring your sensitivity down to a zero level at large scale, you will not, even with a polarization and a temperature anisotropy, it is very hard to detect a suppression beyond certain level. For example, you can see that we can get up to 2 sigma evidence or 2 sigma support for a suppression for certain model, but for other models these are even lower. So it will be very hard to detect a primordial suppression even with a cosmic variance limited survey. However, wiggles that are located in the intermediate and the small scale, such as WWI B, C, or D, as you can see here. So this is WWI and these are WWC and D. As you can see that these are the wiggles that are located at the intermediate and the small scales, corresponding to the scales after the first acoustic peak of Planck of CMB, what you can see is that the zero line can be rejected with a high significance if such power spectrum actually represents the actual history of the universe, actual history of the inflation. So since we are going to improve on the small, intermediate and small scale data compared to Planck with core, we will be able to detect if they are present. So we tried to do another analysis with the features that can be detected in future is with Euclid-like data. So Euclid, as Fabio mentioned, Euclid is going to be a galaxy survey, and it is going to be launched, I think, in 2022. And these are the it is going to detect the spectros millions of galaxies in its spectroscopic detectors, and maybe billions of galaxies in the photometric detectors. And why this is important? Because the galaxies do arrange themselves in the same manner in which the CMB is arranged, because the CMB gets its gets its information from the primordial power spectrum. So the primordial power spectrum dictates what power will be there at what scales. Similarly, depending on that, our universe has evolved. So all the gravitational collapse has happened and everything, and we got the galaxy cluster of galaxies and stars and all that. So at the galactic level, or if we count the number of galaxies and get the correlation between the galaxies in the sky, we can say that this follows the same distribution of the primordial fluctuations. So we try to do this analysis that with Planck, we try to compare Wiggly Whipped inflation in this paper, and try to address which type of features can be detected with the help of Euclid. So as you can see that Planck, with some features that are shifted towards the right or towards the smaller scales, has some significance in detections, although these are the toy models, or these are the fiducial model, as I said. This is not a comparison with the data, with the real data. So you can, if you get a constraint like this, you can get 20 to 40% improvement, or even more in some certain cases, on the constraint on the primordial features if you add Euclid to the CMB surveys. Definitely, when Euclid is going to give us data, there will be other small scale surveys as well. So the figure is likely to be improved. If again, I always say, if these features represent the true nature of the universe. So to summarize, as I mentioned before, is that the baseline model, power law, that is resulting from a strict slow roll inflation, it is consistent with the data at all scales. There are certain hints of the fluctuations at L equal to 22, 200, 300, and 750. So with the present data, the features are not detected at high significance. However, the hints are strong. Why the hints are strong? Because the features are presented almost many frequency channels which cover those scales. Also, some of the features are present even in the small scale measurements like Atacama Cosmology Telescope, which just came recently. So with two independent type of surveys, you are getting a similar feature. If they are not statistical, fluctuations, they may hint towards new physics. So with the future CMB and large scale structure data, we can detect the primordial features at intermediate and small scales if they're present, which will lead to a detection of the physics beyond the standard slow roll inflation. However, I would like to stop with this pessimistic remark that the large scale features, however, cannot be detected beyond moderate significance. So even with the CMB and large scale structure data. So with that, I would like to stop. Thank you.
Okay. One of the questions is that how important is cosmic variance while one says that NS is blue tilted on large scales?
So you mean yeah, I've seen.
You're able to see the questions in the chat box.
I'm able. However, NS is red. Maybe the question refers to a blue deformation at the larger scale. So in this case, I would say that data are important from CMB temperature power spectrum, and for the error on this deformation, yes, cosmic variance is important, I would say. If the question instead is on NS blue, I mean, then NS blue is ruled out through all the wavelengths, is ruled out at very high significance. I mean.
Okay, okay. There is another question from Robert. Are the limits you gave for the isocurvature perturbations limits on the amplitude when scales enter the Hubble radius or on the initial amplitude? Example, at the time of amplitude at the time of reheating.
So the constraints I'm reporting are on the fraction on the isocurvature contribution with respect to the sum of the curvature and isocurvature. So, and that amplitude is basically the coefficient in front of the regular isocurvature initial condition is the radiation dominant era. So it can be related to the, obviously, to the power spectrum of the generation, but during inflation. But then you have to assume all the history. I mean, so the constraints I'm reporting are on isocurvature, on the coefficient, dependent on K, obviously, of the isocurvature mode in the radiation dominant era after Big Bang nucleosynthesis, let's say, when we initialize fluctuation in the Einstein-Boltzmann codes.
Dhiraj?
Yeah, I think it is for Fabio, because I think Sriram, you are asking from the observation.
Asking at the larger scales at very low multiples.
Okay, at very low multiples. Okay, so I do not know what I have not gone through completely the Planck's. Okay, so let me start my video. Okay. So I haven't gone through the complete analysis of Planck on the non-Gaussianity. I think Planck also had done some joint estimation of the power spectrum and bispectrum, right? So I think probably Fabio is the best person to talk on that.
Yes, I think that, I mean, this joint estimation is for global models in which you consider linear or logarithmic wiggles on all scales. I think, I mean, this question may be also connected to the actual result of 2018, in which constraints on the running of the bispectrum was also studied. So I think that this is an interesting area to think about. Maybe also Nicola can add, can reply if he's connected.
Professor Nicola Bartolo, are you there?
I can ask Nicola if you would like to comment about it.
Yeah, I couldn't unmute. Sorry, myself. So thanks
Sure.
a lot. No, I can just add a few comments on this in the sense that for sure non-Gaussianity can help. Let's say you can, as it has been done within the last Planck data analysis, you can perform a full data analysis of different kind of oscillatory features in the bispectra by themselves, which actually are predicted by the same models that have been discussed in the last two talks. And it definitely can help in the case where, and that's why these joint power spectrum and bispectrum analysis are very important. It can definitely help where you have a specific, to test specific predictions of a model in which, you know, let's say once you give the prediction for the power spectrum, what you would expect for the bispectrum. That is very important to test because of course this would also help to eventually to let's say alleviate the so-called look elsewhere effect when you do this kind of data analysis for oscillations. So the fact that essentially especially for example, data analysis for bispectra, analyzing frequencies and phases for these oscillations on a very large number of models, you could pick up some statistical significance for some frequencies or some phases. But of course, you have to correct these properly from a statistical point of view, because these are kind of, let's say, fluctuations that you expect in your data analysis. And you can really alleviate this aspect of the data analysis if you are testing a specific models where you know what are the predictions for the power spectrums, and given this prediction for the power spectrum, you know what are the predictions for the bispectrum. So for sure, from this point of view, the joint analyses are, I think, crucial in order to get some more insight inside these issue of oscillatory features.
Thank you. Thanks, Nicola. I don't see any other questions in the chat box. And also there are no hands raised. So if there are no other questions, Fabio, can I ask a question myself to you?
Sure.
Yeah, so I just want to get some idea about, you were talking about the future prospects in terms of constraining inflation and all that. So what are the sort of projective limits that we are looking at in terms of the tensor to scalar ratio by means of, let's say, CMB stage 4 experiments and other, let's say, even space-based experiments? I mean, on the R.
Yes. So, so I quoted two examples.
Mm-hmm.
Okay, one example is was Simon's observatory, since is the first one in the timeline, and is in few, let's say 3.2 from the science book, in 10⁻³ after foreground marginalization. For Lightbird, the figure of merit is somewhat 10⁻³, but in this budget, there is not only foregrounds, but also margins for systematics beyond, obviously, cosmic variance and the statistical error. So at the moment, we are discussing about roughly 10⁻³. There are more, let's say, ambitious project or concept as PICO, or the concept in reply to the Voyage 2050 ESA call, which goes in the territory of 10⁻⁴. Actually, PICO kind of put as a figure sigma of R in the ballpark of 10⁻⁴. Obviously, foregrounds are more or less 2 orders of magnitude larger of these numbers of, and also there is obviously the parasitic signal of the B-mode polarization from lensing. So, did I reply to this?
Yeah.
Questions?
So,
I'm sure that Tarun will explain what is the target of CMB Bharat.
Right.
I haven't covered this, obviously, because Tarun will speak in the next days.
Yeah. Thanks, Fabio. I don't see any other questions, and not in the chat or the hands raised. So with this, we can thank both the speakers of the session, Fabio and Dhiraj. Let's thank them.